Okay. So Laura, would you like to just sort of do an initial sort of intro and say about sharing camera and that sort of thing?
Sure. Hello, everybody. If you have any questions or anything that come up as we're going through the webinar, if you don't mind putting them in the chat box, we're going to have a Q&A at the end, so we will try and answer them. Yeah, I think we've got 10 to 20 minutes for Q&A, so capturing there. Yeah, the Zoom is being recorded and will be shared afterwards. You're all automatically muted on arrival, so you don't have to worry about muting yourselves. But yeah, in the Q&A, if you put it in the chat box, and if we have enough time, we could invite some people in to share, depending on time. I think that's everything.
Okay, that's great. Yeah, and just to say that we will record the video, and we're going to share it on Dorset Climate Action Network, Dorset Community Energy, Wessex Community Assets. So if you don't want to be seen as part of that video, then please turn off your camera. Okay, great. Okay, so I'm just going to give a very quick background to this series of webinars, and then I'm going to introduce our speakers, John Butler and Paul Rychnovsky. So I'll just share my screen very briefly. Yeah. Okay, so hopefully you can see that. Yeah, so the background is that I'm chair of Dorset Community Energy and I work for Wessex Community Assets. And we got some funding from the Southwest Net Zero Hub through the Community Energy Fund to look at the feasibility of setting up a Dorset Retrofit One-Stop Shop. Most of you will probably know Dorset Community Energy. We've got 200 members, raised about 1.5 million, and put installations on 28 schools and hospitals and community buildings. We do that through share offers and then getting in match funding grants from things like Low Carbon Dorset. Wessex, our main area of work has been around affordable housing and community-led housing in particular. And so the two organizations had a sort of a common interest in how do we retrofit existing housing stock. And then we have a number of other partners that you'll see there that we're working with on this research. And as part of the work that we're doing, we wanted to run these webinars. We're also working with a partner called People Powered Retrofit, which is a national organization which came out of something called Carbon Co-op in Manchester, which is where groups of people with similar houses work together on retrofitting their houses. And it's an approach that we're very interested in. In terms of what's happening in Dorset, clearly it's not just what we're doing. There's a lot of activity across the county. So organizations like Ridgewater are running the Healthy Homes Dorset partnership. You've got Energy Champions in Bridport, the Citizens Advice Bureau, Dorset Climate Action Network, running things like the Dorset Greener Homes project. So we're trying to find where the gaps are and see how we can add value to what's already happening. This webinar, we were particularly interested in sort of sharing some of the more technical aspects of retrofit, and we've only got an hour, so we thought one aspect would be around the fabric of the building and one aspect would be around heat pumps, because we often get questions about things like, I don't understand, you're telling me to deal with air tightness, but we also need ventilation, so how does that work? So we've got John Butler to talk about that, and then with heat pumps again, there's a lot of misinformation, I think, going on around heat pumps. So we wanted Paul to just go into, how does a heat pump work, which I think a lot of people find difficult, including myself. And then this Saturday morning, if you're available, we've got an in-person drop-in event with lots of really interesting people that you can talk to about different aspects of retrofit, from the kind of materials that you might want to use, some of the more technical aspects like heat pumps. If you've got a listed building, we have an expert in that. Finance, we have Lendology that give loans for finance. So please, if you have a chance, please drop in, say hello, and come and talk to some of these experts. So I'll finish there. That's just a bit of a quick introduction. And now I want to pass over to John. So I've known John a long time, and I was really slightly jealous, actually, that John had done one of the MSCs at the Centre for Alternative Technology in sustainability, adaptation, and the built environment. And since then set up a consultancy called Sustainable Building Consultancy. And John works with a wide range of professionals like architects, heritage organizations, builders, etc., giving advice, and also writes a lot of articles and blogs, which are really, really helpful. He's also a certified passive house consultant. So, John, I'm going to pass over to you. I believe you've got some slides, and you're going to tell us all about the sort of fabric, the physics behind a fabric first approach.
Right then. Let me get this on full screen. There we go. Can you all see that full screen?
That's great.
Brilliant. Perfect. So I've put, before I get onto the sort of physicsy bit of a warning that I am quite geeky. This will be a quite geeky talk. There are charts in it, but I've tried to break them up with some nice pictures as well, and I'll try and explain things clearly, and if not, you can harass me in the questions at the end. I've put fabric first with a question mark because there's a bit of a discussion about whether fabric first is the best approach in terms of decarbonising. Some people say you could just fit solar panels and heat pumps and not do anything to the building and reduce carbon by a greater amount. So I've had a look at that to see whether that's true, and I'll go into that briefly and see sort of where the right sort of balance of these things are, or where I think it is, and then get into some of the sort of physics and some of the things, potential pitfalls and things to watch out for with retrofit. This is a thermal image of a house, pretty much to demonstrate the fabric first approach, or what it does. So the darker red colours are where more heat is being lost. The yellow colours are where it's been insulated, internally insulated on that middle dwelling, and a lot less heat is being lost. They've done internal insulation and triple glazed windows. And you can see that big sort of, I don't know if you can see my cursor, but that big rectangle down the bottom left-hand side, the big red bit, is where they've still got the old front door. So you can see the kind of impact of a fabric first approach in terms of reducing heat loss. So I've sort of looked at this from a kind of energy and embodied and operational carbon point of view. So operational carbon is the carbon that's emitted by heating the building, lighting the building, generally using the building. Embodied carbon is the carbon that's emitted in making the things that you use to retrofit the building, including the heat pump. So if you look at this sort of left-hand chart first, the right-hand one is just the same options, but without the existing building because it distorts the graph so much. So this big column here, which is essentially entirely operational carbon, is just from, this is, I should say, this is based on my current house, which is a 3-bed semi-detached masonry cavity pebble dash 1930s building in Bridport. So this modelling is based on that and sort of different things you could do to it. If you do nothing, which is this big column here, that over a 60-year period is kind of 436 tons of carbon emitted just by continuing to heat it with gas. So I would say don't do nothing, definitely do something. This will come over to the right hand side now, which just makes it a bit easier to see. This was first one is just fitting a heat pump. So assuming that the current radiators are suitable to use with a heat pump, which isn't always the case, but can be. So the heating demand stays the same, and just doing that does cause a massive reduction in the sort of 60-year carbon emissions, right the way down to 89.2. So I can see why there is an argument for just doing that. The problem with that is you're only addressing the carbon emissions. You're not doing anything to improve how comfortable that house is, how warm it is, how much energy you need to well, your energy bills, basically. You may even find that increases your energy bills because we're still in a slightly ridiculous situation that electricity is more expensive than gas for heating. So if you start sort of, each of these bars is a little bit more retrofit. The first one here, the 67.7 tons of carbon, is just insulating the cavity, insulating the loft, and making a tiny improvement to the kind of air tightness. And that already reduces it by down to 67 or nearly 68 tons over a 60-year lifespan. If you add into that the floor, insulating the floor, putting in triple glazed windows, you reduce it down even further to 46 tons. You can see this red bit is the increase in embodied carbon. So there's a sort of trade-off. You can spend a bit more embodied carbon to have less operational carbon over the sort of 60-year period. This one, I'm assuming mechanical extract ventilation. So I'll talk about ventilation more in a bit, but just briefly, MEV is kind of constant, slow rate extraction, but because it's constant, you're constantly removing the stale air from the house, and that just draws fresh air in behind through vents. The next one over is switching from MEV to MVHR, which is mechanical ventilation with heat recovery. That extracts stale air from all the wet rooms and supplies filtered fresh air to all the living spaces. And they go through a heat exchanger. So the heat is transferred to the supply air. So that saves you a bit more energy and has quite a big increase in comfort, but not a massive change in the sort of overall carbon emissions. And then the final one is just making further improvements to air tightness and adding external wall insulation. And again, you can see there's a reduction in the overall carbon, but it's not massive. So I think essentially what I'm saying is there's kind of slightly diminishing returns, but it's definitely worth adding in insulation and not just doing the heat pump. Another important point is how quickly these options end up being lower carbon. This is just the same information, but cumulatively over a 60-year period. So this green line heading off kind of into the sky is the do nothing one. That's just continuing to heat this. You can see that each year the carbon emissions get bigger and bigger. As soon as you go to just the heat pump, there's a massive drop in the emissions. But what sort of is interesting for me, essentially, if any of these lines went higher than the heat pump line at any point, that would mean they were causing higher emissions at that point in time. But within sort of 3 years, all of the retrofit options are lower carbon than, or causing less carbon emissions than just switching to a heat pump. So all of these have a heat pump as well, and some insulation. So this is sort of a long-winded way of saying I think it is worth combining insulation with a heat pump, but you don't necessarily have to go straight to a deep retrofit. Even quite a gentle one will cause good improvements. This, I won't go into this too much actually, but the red mark is the heating demand. So how much heat energy you need to put into a building to maintain the kind of internal comfortable temperatures. The blue bar is how much energy you use to provide that, essentially. The key point here is you can see for the heat pump only option, the heating demand is exactly the same, but the amount of energy you need to provide that is massively reduced. But it's only once you start reducing the heating demand by making fabric improvements that the sort of energy you need reduces a lot. And that's important because if we decarbonize, if we put lots of heat pumps in, then the demand for electricity grows. So we need to reduce the demand per house so that there's essentially enough electricity to fuel all these heat pumps. Plus you get these comfort improvements. This line at the top is the calculated average internal temperature if you heated all of these scenarios to the same heating pattern. So your heating system was on for the same length of time, putting out the same amount of energy every day. How warm is your house? So it starts at kind of an average of 15 degrees, which is probably about right for this house. And then by the time you've done sort of more retrofits options, you're getting up to an average of 20 to 21. with a lot less energy and the same heating pattern. So it's the heating would be on the same amount of time, but it will be putting out less heat. So essentially what that means is you're a lot more comfortable. I find a kind of simpler way of looking at this is the green bars are kind of essentially what size heat pump output you would need for these. So you can see the heat pump starts at kind of about 11 kilowatt heat pump and goes right the way down to 3. There aren't many 3 kilowatt heat pumps in existence, actually. It's still a bit of a problem with low energy houses that the technology needs to catch up, but you can get kind of 4 or 5 ones which would suit these last 3. But the point being, a smaller heat pump is cheaper to run, so your heating bills will be lower. They're much lower carbon to produce, and I think they're cheaper to buy, but Paul will know probably more about that than I do. So my point then is some fabric and heat pump first, and then you can always go further and phase in sort of later stages of deeper retrofit. But even just the cavity and the loft, so quite basic insulation, a little bit of improvements in air tightness and working on your ventilation will give you a warmer home and greater comfort and a kind of healthier internal environment. And that in turn means you've got a smaller heat pump with lower running costs and lower carbon. And as you go to deeper retrofit, essentially all of those benefits just get greater, but sort of only up to a point. There is a bit of a sort of diminishing returns. So onto the physics bit, the warmth, cold, damp and mold, they're all kind of related to physics, and any Douglas Adams fan will know that there's sort of the importance of the interconnectedness of all things. Because each of these elements, the warmth, the cold, the damp, and the mold, if you do anything to improve any one of them, you'll probably improve the others. And equally, if you do anything to make any of them worse, you'll make the others worse. They're all completely interconnected. So it's really important to kind of look holistically. One of the main reasons we have problems with damp and mold in houses is just the amount of water vapor that we put into them. You've got kind of existing humidity in the air that comes into the house. And then just by living in it, you're introducing a lot more water. So this chart is the kind of average daily moisture production for a family of 4 in litres per day. And when it says occupants, what that really means is just breathing. So just by being in the house, you're putting in 3.9 kilos, 3.9 liters of water a day, and then cooking adds some, drying clothes, bathing, cleaning, all of these add water. So you're looking at 10.4 liters of water per day just from living in the house, just from using it, from sort of going about your daily activities, really. So that's quite a lot of water. And if you don't remove that water, then it will eventually condense somewhere, or if your surface temperatures are colder, then it's more likely to condense. So sort of bear all that water in mind, or the fact that it's all there, through the next few slides. Heat in buildings is transferred mainly by conduction, so that's being conducted through the building fabric, or convection, which is ventilation and infiltration or drafts. Both of these get called ventilation sometimes, and I'm wary of this because really the ventilation is the air movement that you want. It's your supply of fresh air and it's your removal of stale air. Infiltration is kind of air blowing in through nooks and crannies in your building and little cracks around windows and things. And generally you don't want that, because that will pick up kind of contaminants through the cracks in the buildings, and if there's mold in there, it will bring mold spores in, so it will cause sort of detrimental internal air quality. Sort of in a matching fashion, moisture in buildings is transferred mainly by convection. So again, that's ventilation and infiltration, and a small amount of diffusion. So some is just sort of drawn into the fabric of the building. You get mold most frequently where either conduction is higher, so heat losses are greater, or ventilation is lower. And essentially that's because the air has such a capacity to carry moisture, where there's less air movement, the moisture will sort of stay built up on your surfaces or in the air around those sort of corners, which is why you tend to get kind of more condensation in the corners of rooms, because there's just less air movement there. So there's less moisture removed, which gives you higher humidity and makes condensation more likely. And kind of at the same time, where conduction is higher, you've got, or essentially where there's less insulation, you've got higher heat losses, which gives you lower surface temperatures, and that increases the chance of that moisture condensing. And you get mold growth where both of these things are happening, and the condensation is there for a sort of extended period of time, and then mold will start to build up. And that again has sort of detrimental effects on your building and on you living in it, because mold spores are not good to be breathing in. So you can deal with that by improving your ventilation, supplying fresh air, extracting moist, stale air, and gap-free insulation is really important. You want a continuous insulation layer, and you want to make it airtight. Tim mentioned the importance of kind of airtightness and ventilation. You very much need both. If you make your building airtight without sorting out ventilation, again, you'll have really poor air quality. So essentially, mold is prevented by all the things that make a warm, comfortable, and easily heatable house. So it is what I mean, they're all interconnected. They're sort of addressing everything, addresses other issues at the same time. And I was putting this together, that reminded me of this cartoon. What if we create a better world for nothing? So it's kind of, you can start off just looking at mold and end up with your whole house being much more comfortable and reducing your carbon impact at the same time. So how do you improve ventilation? I mean, the obvious one is if you only have, if your ventilation is provided just by opening windows, make sure you open them. Quite commonly, people don't open them as much as they should, understandably trying to retain heat. This is partly why windows aren't the most reliable source of ventilation in a sort of meaningful supply of fresh air and removal of moisture way, because there is that conflict immediately between retaining heat and needing the ventilation. There's sort of quite good studies done now that show that just relying on windows is not the most effective form of ventilation. It also gives you the greatest heat losses. Looking at the retrofit options I modelled on this house in the sort of earlier in this talk, if you switch to the mechanical extract ventilation, that reduces the overall heat demand by about 12%. It's more effective at actually providing ventilation, and you can still open windows anytime you want. That's a crucial thing, that sort of, there's a myth around energy efficiency that you can't open the windows when you've got a ventilation system. It's in fact, you can open them just as much as you want and the ventilation system will still be effective, particularly actually with mechanical ventilation and heat recovery, because it's balanced. The supply air is the same volume as the extracted air. You can sort of open doors and windows without that interfering with that. They'll still recover more energy than they use, and that reduced the heating demand of this house in my modelling by a sort of 30% compared to windows only. So that ventilation is really important, because it removes the moisture and reduces the chance of it condensing because the moisture is not there as much. And then you add your insulation and your air tightness, and then you've got warmer surface temperatures and less chance of condensation anyway. This is some internal insulation in one of my cousin's houses, or the house of one of my cousins. You can sort of see they've leveled off the surface. They're fitting these wood fiber boards on the walls. There's very little gap, or ideally there's no gap. I think these are tongue and groove boards, so that sort of makes less gap between them. And this tape around the window, this blue line next to the window frame, is air tightness tape that's sealing the window to these boards. And then when they're plastered, that will become a kind of complete airtight system, essentially, the windows and the boards and the plaster. So again, there's no gap there. This middle photo is kind of looking down into where the first floor structure, the upper floor structure, joins the external wall. And this is a bit that can quite easily be missed. You can see they've taken off the floorboards, and the insulation actually carries on right the way from the ground floor, right the way up through the floor joists. And that's really important, because if you've got a big gap in the insulation, you're losing a lot of heat there. I've put no gaps between or behind, because there's sort of, if you think of the classic kind of insulated plasterboard that's stuck on with sort of dot and dab approach, where there are blobs of plaster gluing it to the wall, what you end up then is an air gap, or you can end up with an air gap depending on how thoroughly it's been glued. That air gap Usually moist air will find its way into it. It will then condense because it's colder behind the insulation, and you get mold building up there that you don't know about. And then some air will inevitably flow through that and again affect your internal air quality. You also get a bit of thermal bypass where the air is moving behind the insulation freely and almost making your insulation pointless. I'll come back to the gaps in a moment. I'm just going to quickly have a look at thermal bridging, which is sort of related again to this bit in the middle. This is looking at, again, sort of a bit like my house, you've got cavity wall insulation. What people often miss is the outer skin of the cavity stops short of the inner skin. So if this sort of rainbow at the top is the roof loft insulation, you've got the outer wall, you've got a layer of cavity insulation, and then the inner wall. And there's a big bit that's hidden in the soffit that has got no insulation at all. And the surface temperature on that is 6.3 degrees in sort of winter conditions, which is really low and definitely a condensation risk. If you just insulate that area of wall and extend the roof insulation over, that surface temperature goes up to 16.9. So immediately you've got reduced condensation, less mold growth, and a lot less heat loss. So all of those things, again, working together. This is a really important point that I think a lot of insulation installers are, I think, unaware of through no fault of their own. But if you have a 1 mil gap between two bits of insulation, you're going to get 800 grams per meter square of water per day entering the fabric of the building through that. Without the gap, you get 0.5. So essentially, a 1 mil gap will put 1,600 times more water into the fabric of your building. And then you have however many 1 mil gaps amplified over, the edges of each insulation board. And that's quite a lot of moisture, which will then find the cold surfaces and condense and cause mold and potentially decay. So those gaps are really important to avoid. In terms of heat loss, you've got 5 times greater heat loss per meter square from that 1 mil gap. And again, that's amplified by every gap that you have. Sorry, excuse my croaky voice. I've got a cold at the moment. So yeah, the gaps lead to significant heat loss, which puts a lot of moisture into your building fabric, which you've then got to try and get rid of somehow. That leads to condensation on and in the fabric, which leads to mold growth. And that in turn can either cause decay in your building or poor air quality, because where air can get into those gaps, air will also get blown into the building the other way. And that can then pick up those mold spores and bring them into your internal environment. I've just realized I'm on 21 minutes. I've just got a couple more slides and then I'm done. Sorry, this is a lot of information I'm throwing at you, but it's just to try and give an overview. I don't expect it all to stick, but hopefully sort of some of it will go in. So back to this again. If you insulate, make airtight and remove drafts and ventilate properly, you're improving both energy efficiency and health. And a kind of side effect almost is that your carbon emissions will be reduced as well. If you can only do 2 of these, I would say kind of removing drafts and ventilating properly will, in terms of health and internal air quality, be the most important ones. Making a building airtight will reduce your heat loss a lot, but ideally do all 3, even if it's just sort of quite gentle insulation, as it were. Final thing to point out is vapor permeability. This is a massive subject that you can do entire courses in, so I'm going to try and just give you the very basics in 2 slides. Essentially, particularly in older buildings, you need to allow moisture that's got into the building to get out again. And what tends to happen is in winter, when it's warmer inside, any moisture is sort of pushed into the wall. In the summer, when there's maybe sun on the outside of the wall, that warms that up and pushes the moisture back in. If you have an impervious layer, like sort of foam insulation or airtight membranes that are literally just a plastic sheet, the problem then is that moisture is trapped. It can't get out. So it's really important to use materials that manage that. This is just the last slide, a quick illustration of other ways moisture can get into the building. So this is that diffusion. It's basically drawn through, say, an internal wall, even if you've got sealed ceilings everywhere else. And this graphic on the right hand side is just, you can sort of repeating what I've just said really, but you can buy membranes that will prevent water getting into the structure in the winter and will allow it to dry out in the summer. So it's just making sure you use the right sort of materials and the right kit. And that's me done. So I will stop sharing. There we go.
Thank you,
I'm
John.
still sharing, aren't I? Hang on. There we go.
Thank you. Wow, that
Oh,
was really, that's quite a challenge to get through that in 20 minutes.
I hope it wasn't.
Really, really helpful. Thank you so much. So I don't think we got any questions yet in the chat, but just to say, if people do have questions for the end on the basis of that, then put those in the chat and Laura and I will monitor those and pass them back. Yeah, but thank you so much. And I think it was really good that at the beginning, you were talking about the intersection between this understanding of the fabric and then how that might work with a heat pump. So it kind of leads on perfectly for Paul. And Paul is now going to explain to us how heat pumps work, which is another really important, underpinning, I think, of retrofit. So passing over to Paul. So Paul, it's interesting. I know Paul, so I'm sort of thinking, how do I introduce Paul? So Paul is a refrigeration engineer who's actually done a lot of work in commercial buildings. And what's really interesting about heat pumps is that they're effectively reverse fridges. That's my very, very basic understanding. And so actually refrigeration engineers often have a much better understanding of how heat pumps work than plumbers who aren't trained in the physics of heat pumps. So I thought it'd be really good to have Paul explain to us how heat pumps work. So Paul, over to you. I don't know if I've missed anything in your, I'm sure, broader than just being a refrigeration engineer, but thank you for joining us.
No, that's pretty good. Thank you very much. Thanks, John. I really like that first graph showing the effect of a heat pump being fitted to a building, showing the massive reduction in carbon dioxide emissions. Right, okay, I've been a refrigeration engineer for 15 years. And as Tim said, most of my work is involved in the industrial area, mainly on farms. But I have fitted domestic air to water heat pumps and air to air systems. So we'll have a look at those as we go along. Now, I thought before we delve into the complexities of heat pumps, we'll have a quick sort of look at where we currently stand with heating domestic properties. So I'm just going to share some slides. I'll bring these up. Bear with me a second. And hopefully we're there. Can I have a thumbs up from somebody just to tell me that that's okay?
Yeah, that's good.
Brilliant. Thanks, Tim. So at the moment, this is how we stand heating most of the UK's properties. Obviously, I think it's something like 80% of properties in the UK are heated at the moment with gas or oil-fired boilers. Now, obviously, if we're heading to net zero by 2050, those are all going to have to go. But there are things we can do in the meantime, because what we don't want to be doing, obviously with embodied carbon, and especially as people have fitted, maybe had new boilers fitted in the very recent past, is we don't want to be ripping those out. So we have, I mean, the average gas and oil boiler probably lasts 20 years. So in maybe some of the ones now that have been fitted in 20 years time, that's when we should be looking at replacing those. But what we can do is those that are already in existence, we can make much more efficient. A large percentage of gas boilers, although it says they can be up to 95% efficient, very rarely run at those efficiencies, mainly because they're usually massively oversized for the properties they go into. This is a cause because of the type of boiler we have fitted, which are these combi boilers, which have to be so big to provide the copious amounts of hot water that most people require. But you can increase their efficiencies dramatically by reducing the flow temperatures in your radiators in a house. And this is a good precursor to seeing whether your house would be suitable with minimum disruption and conversion to run on a heat pump. So if you turn the flow temperature to your radiators down on your gas condensing boiler and your house still stays warm, you can start gaining massive efficiencies on how that boiler works, because it goes into what's called condensing mode, which means you've probably seen it as you walk around most towns and villages when it's cold and you see plumes of steam pouring out the side of people's houses. Well, that's all wasted energy. And all that steam really wants to be condensing inside the boiler, so we get the maximum amount of energy back into the heating system. Anyway, so we'll move on quickly, otherwise we'll get dragged down into boiler physics. Moving on to biomass-fired boilers. Now, these seem to be very popular with reducing carbon a few years ago, but they've gone out of favour because a lot of the feed stuffs for these biomass boilers come from unsustainable sources, and when you look at the actual carbon output, the chance of that carbon being replaced in the near future is very minimal. And the other problem being biomass boilers, even the very, very efficient ones, produce a lot of particle pollution. And in fact, wood burners and wood-fired boilers, pellet boilers, are now produce, I think it's a quarter of our particulate pollution, and in fact produce more particulate pollution than the road haulage industry. So it's not something that unless we're in very specifically, maybe very rural areas, you'd want to be looking at being fitted. And I know a lot of urban areas now are looking at banning wood burners and wood-fired boilers completely. So that really leaves us with the bottom two options. So electric boilers, heatage and storage heaters, they are 100% efficient. They can't be anything but 100% efficient. So for every kilowatt of electricity you push into it, you will get 1 kilowatt of heat back out. And they do have their place in reducing carbon emissions. And in certain situations, perhaps in very, very efficient houses or situations where heat pumps can't be fitted, then this may be an option for very few situations. And then we move on to the bottom one, which will be electric heat pumps. And as we can see here, they can run between 200 up to 500% efficient. So basically that means for every 1 kilowatt electricity you push into it, you will get between 200 and 2 times and 5 times the amount of heat coming out. Now that 200% efficiency is the very worst scenario. And usually that's when you use a heat pump to heat up hot water. So what I'll do now is to move on, and I will try and tell you how a heat pump actually works. So yeah, sorry, we'll just look at this very briefly. Domestic space heating currently produces 14% of UK greenhouse gas emissions. And there, so yes, we've been that net zero. So we're looking at a transition to heat pumps, which was similar from when we went from open coal fires 60 years ago to central heating. So put it basically, a heat pump moves energy using gas compression. That's all it does. It doesn't produce any heat itself, not in any meaningful way anyway. So we'll move on to this nice little picture here. Now, this is a diagram of probably the most common type of heat pump you may come across, which is what's called a monoblock system. Now, this means that the guts of all the operating parts of the heat pump are all within one single unit. And these are probably 80 or 90% of the ones that you'll see fitted outside houses at the moment. Now, a heat pump, it needs to extract heat from somewhere. Now, on the left here, we have what are our three most common sources of energy. So that will be external air, groundwater, and the ground. So that would be, obviously, external air is self-explanatory. Groundwater would be if you live near a river or a lake, and the ground would be either if you have a large enough field or paddock, you can lay your coils into the ground, or you can drill a deep borehole. Now, most people go, well, how do you extract heat from fresh air? So we'll have a look at how this little system works here. So this is the refrigeration system. and it's a closed loop. So we'll start somewhere, which will be at the compressor. Now, the compressor is a simple pump. In fact, the early types of compressor, and we've had refrigeration compressors around for at least 100 years. The early ones were very similar to the piston in a car engine. But nowadays they're a sort of scroll shape, but it's not really important. And they're driven by an electric motor. So what they do is, and this is, hopefully you'll understand this. I still have problems getting my head around it sometimes. We take in gas on this side, and I will have to fill this in. So what we'll do is we'll end up going round and round the loop. So we take in gas from this side here, and this is a cold, low pressure gas, and it goes into the pump and it pressurizes that gas. Now, if you've ever stuck your thumb over the end of a bicycle pump and then pumped hard, you'll know that your thumb, you can feel the heat. So what we're going to do is we pressurize the gas, which forces all the molecules which have energy because they're bouncing around in this gas, and we squeeze them tight together. Now, when you do that and you pressurize the gas, it wants to become a liquid, but it can't because there's so much energy in there that all the molecules of gas are bouncing around. So what we do is we pump that gas into what's called a condenser. Now, this is a heat exchanger, and in an air-to-air system, this would be like a car radiator with a fan on it. And what we're going to do is remove the heat or the energy from those molecules, and that enables them to settle down and come much, much closer together, and they become a liquid. So they condense inside the condenser and become a high pressure liquid. And what we've done is remove the energy from that gas, turned it into a liquid, and we've taken that energy and moved it into our house or outside if it's a refrigeration unit. And then we then pump the liquid into what's called, this device down here, an expansion valve. And all this does is allow the high pressure liquid to suddenly drop in pressure. So basically it's just a very small hole that the liquid squirts through. You then end up with a low pressure, warm liquid. Now, because you've reduced the pressure, this liquid, all the molecules within it want to move apart because you've reduced the pressure, but they can't move apart. They will remain a liquid until they can absorb some energy, which enables them to move apart. Now, this is the clever bit. The liquid we use, or the gases we use inside a refrigeration circuit, have a boiling point of -51. So as long as the temperature from where you are removing your energy is above -51, then that liquid can absorb the energy and then become a gas again. So that's what happens. That's why you can extract energy from, even on a very cold day where it's -5, -10, you can take that energy, allow the low pressure liquid to become a gas again. It takes the energy from the air and it goes back to the compressor. The compressor squeezes it down again to a high pressure, high temperature gas that we then take the energy out of. It becomes a high pressure, low temperature liquid, and round the system goes. So I hope that's you can get, because I still find this quite a difficult concept to get my head around. It's quite complex thermodynamics, but that's how it works. Tim's got a nice little video that lasts 50 seconds that I hope he's going to show at the end of this, because it makes my talk rather redundant. So we'll move on. Anyway, so types of heat pump. So quick look. These, for those of you who haven't seen them, I thought I'd find some more interesting pictures of air source heat pumps. These are all domestic monoblock systems. So they have everything needed inside the unit. And these are the types of unit that are very popular at the moment because they can be fitted by a plumber, that you don't have to get refrigeration engineers involved. And so they will be taking energy from the surrounding air, and you will take 2 water pipes to these units that will then take the heat that's been harvested, from the external air, and then it's pumped into the house and will either go to radiators or underfloor heating. Now, the other type of heat pump we probably come across in most common domestic environments, and I'll include offices and shops in this as well, is air to air. Now, this is where we take the warm air from it harvests the energy from outside, and then rather than moving that energy into the water system of the house, so into the radiators and underfloor heating, we take it straight to the condenser. So these units that are inside here is a radiator which the refrigerant liquid runs through. It condenses inside there and releases its heat through a fan and blows it straight into the building. Now, one of the advantages of these for retrofit, and I think these will become a lot more commonly fitted over the next few years, is that they can, first of all, go into buildings that have no previous heating systems in, and also they're much cheaper to fit. Now, one of the reasons these haven't been included in government schemes so far is they're commonly used for cooling. And in the past, the government were not very keen on people using air conditioning or cooling, because you're actually placing a greater carbon burden or producing more carbon emissions. But very recently, these units now can be locked to heat only. So there's a possibility when the boiler replacement scheme is reviewed, that air-to-air heat pumps will become included under that scheme. Where was I going to go with this? Oh yes, that's the one thing. If these are fitted at the current time into houses, as long as they're used for heating, they are VAT free. It's a little loophole that the government left for installers to exploit. So one of the questions that lots of people always ask is, can a heat pump heat my drafty old house? And the answer to that is a simple yes. A heat pump can heat any enclosed space, as long as, and this is the really critical thing, and this is the thing where it just doesn't happen properly, is a heat loss calculation is done of that space. So that means a person needs to come into the property, and they will measure very precisely the dimensions of the property, its fabric, its existing insulation, the types of windows and the size of them, the doors, even things like whether there's a chimney there. So they'll be looking at how often the air is changed. And this survey process takes usually between 2 and 3 hours minimum. And from that, they will be able to work out how many kilowatts it requires to produce or keep that room or house at a set temperature. So, for example, in, say, a 3-bedroom house, you would say the bedrooms would be at 18 degrees, the living room would be 21, I think the bathroom is 21 as well, and the kitchen is 18. So from that, you could, and a ballpark figure would be, on an average 3-bedroom sort of 1980s detached house, you'd be looking at about 6 or 7 kilowatt heat loss. And that's done, that calculation is usually worked out at an outside temperature of about -2. So that's the main important thing, that heat loss calculation is done, and then a heat pump is sized to that heat loss. So if your heat loss is 7 kilowatts, you will install a heat pump that would be a 7. Now, the other critical thing is how the system internally is designed. So one of the really important things with heat pumps is the lower the temperature they can run, the more efficient they become. Now, modern heat pumps can be connected directly to old radiator systems. It can be done. And you can run heat pumps at very high temperatures. So they can be running at the same temperature as a good old-fashioned gas boiler. The problem being is they won't produce the efficiencies to make the major savings. So you can connect a heat pump direct to radiators, run those radiators at 50, 55 degrees flow temperature, but you will only get a efficiency of maybe 2 to 300%. If you can reduce the flow temperature, and the lower you go, the greater the efficiency. And this is where adding insulation into a building would enable you to run at lower and lower temperatures, the better and better the efficiency gets. So what can be done, and which makes heat pumps an interesting proposition, is you can have your old drafty house with poor insulation, and as long as you let the installer know that you are going to add in the future better loft insulation, improve the windows, insulate the floor, they could probably work out a heat pump that would turn itself down low enough that when you have done that, you could slowly turn down the temperature at which you heat your radiators up to. So they can be very adaptable, but they have to be, as long as you let the installer know exactly how you want your system to work and what you're going to do to your property at a later time, then you will get those efficiencies in the future. The other thing, which is often where heat pumps get their very bad press from, is that some people have them fitted and then use them incorrectly. Now, you can't treat them like a gas boiler. They are what's called low and slow heating. So we've lived with gas boilers for 50 years, where you come in from work and maybe 10, 15 minutes before you get in, your timer would turn the boiler on and you would blast heat into the house, and you would arrive and the house would be nice and warm. Now, heat pumps, they can do this, but again, they will do it very, very inefficiently and use lots of electricity. What a heat pump likes to do is just trickle heat into a house very, very slowly. So what some of the heat pumps I've come across where people have had lots of problems with them is where they've tried to run them on a timer. Rather than letting the heat pump run for 24 hours a day at a much lower temperature, they have it switch off at night, and then the heat pump has to ramp right up in the morning, and then it turns back off again, and it never reaches peak efficiency. The other thing people do is also, and this is perhaps maybe John will back me up on this, is in the past people heated their homes room by room, and this was fine where you had a gas boiler that was vastly oversized, so you could have one room that was very hot and maybe not even heat another room. Again, heat pumps don't like this because you are heating at very much lower temperatures. It's much more efficient to heat the whole building as one single envelope. And one of the good side effects of this is that it dramatically reduces drafts. And actually, I've experimented over the last few years so I'm in a transition period at the moment where I have my main part of the house. I still have an old-fashioned gas boiler, and I have an annex where I fitted a heat pump, and it's been quite nice. So I can compare how the two work together. In the last few years, I've been heating my house at very, very low flow temperatures using my old gas boiler. It's massively improved the efficiencies, and it's also reduced all the drafts in the house. So although the overall house temperature is lower, it feels much more comfortable. And it's also done all those other things, like John said. It's reduced the mold problem, because I live in a 200-year-old solid stone-walled cottage, and it's actually ended up using the same amount of gas, even though the house is far more comfortable and remains at a much more stable temperature. Right, move on.
Paul, we've got 3 minutes.
Okay.
So perhaps if you finish this quite quickly, there was a question about what do you mean by flow temperature being as low as possible. That might be quite a complicated one to deal with.
Okay. Yeah, well, let me just do this, because we're right at the end. This is probably the most important thing that people need to know about. This is happening this year. We've got new permitted development rights, which basically the government have just got to rubber stamp, so basically put through the legislation programme. So hopefully later this year there'll be parliamentary time. In the past, lots of people had problems fitting heat pumps because councils have said they can't fit them. So in the past, you had to have the outdoor unit had to be within 1 meter outside of 1 meter of the edge of the boundary So in very small gardens, this was causing all sorts of problems with locating the outside unit. The other thing that's important, they've increased the maximum size of the heat pump outside from half a cubic meter to 1.5 cubic meter. Now this enables the manufacturers to make the outside units much bigger, which means they can fit more sound insulation into them and fit bigger fans. And bigger fans don't have to turn as fast, so the noise levels become much less. This is one of the major problems with heat pumps, especially in very crowded urban areas, is neighbors don't like the noise. And the other thing is the number of heat pumps permitted has gone from 1 to 2 if you live in a detached house. Now this enables you to run what's called cascade heat pumps, where you can have 2 together. So when it's so you can have 2 identical heat pumps. So when the weather's warm, you just run 1, and as it gets colder, you can then run 2 so they can both work efficiently together. So I think, let me have a look. I'll just see what the last slide is. No, I'll leave that on. So sorry, Tim, can you just remind me what that question was about the heat flow?
Yeah, it was, what do you mean by flow temperature being as low as possible? How do you control it for an air source heat pump?
Okay, well, it's air source heat pumps. There are 2 ways of controlling an air source heat pump. There's the traditional way where you would have a thermostat in the room, and you would say, I want my room to be 21 degrees. And the heat pump would run flat out until it reaches the 21 degrees, and then it would switch itself off. And that's very inefficient because the heat pump will run as hard as it can to achieve that temperature. Or it can be run in what's called weather compensation mode. And you can actually do this with gas boilers as well. And what that does is it takes the outside temperature and your required inside temperature, and rather than just turning the heat source on full power, it will turn on just enough to get that room to that temperature in relation to the outside temperature. So obviously, if it was -5 outside, the heat pump would produce maybe a flow temperature of maybe 50 degrees. It would be very inefficient, but it would only be while the outside temperature was at -5. And then maybe on a day like today, when it's 10 degrees outside, it would send the flow temperature going to the radiators, the underfloor heating might only be 20 degrees. So what happens is you end up with, over the whole of the heating season, so let's say 200 days in the year, there might be 20 or 30 days in the year where the heat pump is not running very efficiently. It might only be running at 200% efficiency, but at the either ends of the season, so in the spring and the autumn, you may be getting your 500% efficiency because the heat pump can turn itself up and down according to the external temperature. And you can copy this manually on your boiler if you know what you're doing. And I'm saying you need to know what you're doing. Don't just go and start prodding buttons on your gas boiler, but you can turn down your flow temperature as you get mild days on your gas boiler, and turn down the temperature of the water that you send around the system. And gas boilers are the same. The lower the flow temperature and the lower the temperature of the water returning back to the boiler, the more efficient the boiler becomes. I hope that's explained it.
That's great. That's wonderful. Thank you so much, Paul. It's yeah, I mean, I think we just need to know about, you know, the sort of technicalities of heat pumps, because they are going to become more and more, hopefully, ubiquitous as we go on. So it's fantastic to have this sort of basic understanding. So just I realize we've hit 8 o'clock, but we do have a number of questions in the chat, and maybe we'll just spend 5 minutes going through those. But obviously, if people need to leave, we understand. But we'll be putting the recording online, and we'll send you links to the recording if you do have to leave now. But there are a couple of questions for John that I think would be good to go through. So the first one was from Matthew Collins, and he says, I have a question regarding the protection of floor joists when surrounded by internal wall insulation. I've heard that special tape may be recommended to wrap the joist ends to protect against this risk of interstitial condensation. Do you have any thoughts on this?
Yes, you're right. I skipped over that because I was trying not to go down any more rabbit holes than I already did. But yeah, it's particularly if you're internally insulating around the joists, what happens if the joists are still set in the external wall? The end of the joists are then in a colder zone than they were before. So what you don't want is the warm air from the dwelling, that's the warm moist air from inside the house sort of following the path between the joists and the insulation, getting to the cold zone and condensing, because then it will essentially rot the joists where they're massively structurally significant. So there are sort of two things you can do. One is put something like lime or clay plaster around them that acts as a bit of a sort of moisture buffer. It will soak up sort of excess moisture and then release it later as the sort of surroundings are drier. That works quite well on its own, but even better is to do something like that and seal around with either airtightness tape, or you can get kind of paint on airtight sealant now, which makes it a lot easier, because putting the tape around all the joists individually, you get quicker at it, but it's a lot easier to just sort of paint something on. But yeah, ideally you would air seal them before you put the insulation on, and then again when you put the insulation on, because you also don't want cold, moist air coming in the other way from the wall. So it's, yeah, that's definitely a thing that's worth doing.
Okay. This is a very perhaps Bridport question from Dillis. It says, our 1920s brick double skin detached house has an exposed southwest side and cavity wall insulation. That outside bedroom wall appears wet, and we have developed internal mold inside a wardrobe we constructed there. Cavity insulation was installed by a predecessor. Was it a mistake? We would welcome any advice on treatment, please.
It's one of those, it's really hard to know what's going on without seeing it. There's lots of different things that might be impacting that. It could be a lot depends on what the cavity insulation was, what type of insulation it was, whether that's even a factor or not. I would also, like, if I looked at the house, I would be checking the kind of render or pointing on the outside of that wall. If water's getting in there, it can cross the cavity. So sometimes insulating a cavity can increase the chances of moisture crossing the cavity. There are kind of guidelines on depth of cavity, because we're in a sort of a high exposure zone for wind-driven rain down here. So there's the guidelines sort of change slightly depending on what the system is, but essentially there's sort of a minimum. For wider cavities, it's safer. For narrower cavities, there's more of a risk. If your building is rendered, it's less of a risk, because then the water isn't getting into the wall. If it's a brick or a stone wall and there's maybe cracks in the pointing, like the bits of mortar that join the bricks and stones together, then water can get in there. And in some circumstances, cavity insulation can sort of draw that moisture to the inside, but it very much depends what kind of insulation it is. What I tend to recommend these days is the bonded bead, EPS bead insulation. It's not kind of the lowest carbon, but the impact it has is great. But the advantage of that is water will drain through it. Mineral wool cavity insulation can sort of hold on to the moisture, but it also could be a ventilation thing. If there's not ventilation in the room or the wardrobe, it might just be internal moisture hitting the wall and condensing. But then if it's been insulated, it should have a higher surface temperature. So yeah, it's sort of annoyingly impossible to answer, I'm sorry, but there's many potential factors.
Okay, thank you. And then a couple of questions. Maybe this needs to be the last ones, because I don't want to keep people too long, but the two sort of related. So there was a question for Paul, which says, this is from Mary too. To Paul, did you say you have a heat pump in an old solid wall house? If so, how have you insulated the building? And then a kind of related one from Belinda was that in Lyme Regis, 40% of the buildings are listed or in the conservation area. So most people here think they can't retrofit older buildings or won't get planning permission for changes. And I guess that would include an air source heat pump. So do either of you have anything to say to those two questions?
Shall I go first?
Sure.
Yeah, so I have got an air-to-air heat pump fitted in. So the part of the building I've got it fitted to is a bit of a mess, actually. It's an old single-story part of the house. It's got some single-skin concrete block walls. It's got solid stone walls. It's got some old timber walls, and the only insulation, it's got bog standard double glazing and about 200 mil of insulation in the roof. And that's heated. It's approximately 40 square meters, and it's heated with 3 internal blown air units. And even during, say, it's 1 or 2 degrees outside, it will keep the internal temperature at a steady 20 degrees and be using about 300 to 400 watts an hour. So yes, they will work in almost completely uninsulated buildings, apart from a bit of loft insulation. So it just has to be sized correctly.
Right. And John, do you want to say something encouraging about the fact that we have listed buildings and conservation areas?
It can be complicated with listed buildings and conservation areas, but often it depends what the reason for the listing of the building is. But certainly with conservation areas, they're usually concerned with how the building looks from outside, or how all the buildings together look. So internal insulation tends to be a lot more accepted for conservation areas. I mean, essentially, it's then not a planning permission issue if you're internally insulating in a conservation area. If it's a listed building, then anything you do to it is a planning issue, and that does include internal insulation. But usually the compromise that sort of comes up with listed buildings is to internally insulate on the sort of historical facades, or the ones that are most important, and then you can sort of externally insulate around the back of the house, which unless that's also part of the kind of historical importance. But there are usually ways of, you can still do things, you just have to think about them a bit more carefully, I guess, but not necessarily that much more carefully. Listed buildings is the most complicated, because it does very much depend on what the features are that have led to it being listed, and whether they're internal or external, and usually it's a little bit of both. But there are listed buildings that have been sort of retrofit to ENERFIT, which is the kind of passive house retrofit standard, which is very hard to achieve in terms of energy efficiency. So it can be done, and I think there are sort of simpler things than going all the way to the passive house retrofit that you can definitely do. But yeah, you sort of have to think about it carefully and talk to your planning officers and try and get them on side early when it is a planning issue.
Yeah, but one of those pictures that showed the external heat pump units, they had vinyl wraps of bricks and stone on them, and one of those was from a picture where it was on the side of a listed building, and the planners there had let it through on that understanding that they had a vinyl wrap put on the heat pump. So it can be done, but I guess it's down to your conservation officer at the end of the day.
Yeah, great. Okay, so I'm going to call it to a halt. Thank you so much, Paul and John, for sharing all your knowledge and experience. It's been really, really helpful. As I said at the beginning, on Saturday, we have our, I'll just put it on the screen, come along to the WI Hall. We have people there who have expertise in listed buildings, in heat pumps. And so if you have more questions, that's a real opportunity to come and learn more. And we have, great, my screen is not working anymore, but next Thursday at the same time, we have a webinar with some experts on the use of natural materials in retrofit, an architect and a builder. So I hope that you can join us for that. But thank you very much for joining us this evening. And as I say, you'll get a note for the recording and for other resources as well. So, and thank you, Laura, for doing all the technical work and making this happen. Thank you. Good night, everybody.
Great. Thanks very much.